This is quiz number 7. This is July 28th. James Lewis. That's me. We have our rope wrapped around a disc question. So question number 1. A wire is wrapped around a disc with radius r and mass m is shown. Knowing that the cylinder is released from rest, determine the velocity of the center of the cylinder after it has moved downward a distance s. The answer should be in terms of some of the given variables only. So we have our free body diagram here, and our initial position as s0, which I've written later on as 0. And we have our distance s, our radius r, and our mass m. So we wrote our force diagram just underneath that. We have our force due to tension going upwards, and our mass times acceleration going downwards, and then we have our angular acceleration going clockwise. And I should have drawn that, but we have our coordinate system x, y, and that's going to be plus. Our sum of forces in the x direction are negligible because they don't exist, so we're not going to worry about that. Our sum of forces in the y direction are equal to mass times acceleration, so the sum of forces in the y direction are only the force due to tension, and the mass times acceleration is mass times the acceleration due to gravity. So we're going to star that equation because we're going to end up using that later on. Then we're going to take our sum of moments around the origin equal to the inertia times angular acceleration. Our inertia for a disk is 1/2 mr squared, and the sum of the moments is equal to the force, is the only force that's acting not in line with the origin is the force due to tension. So force due to tension times the radius is equal to the moment, and that is equal to 1/2 mr squared times the angular acceleration, and the radius on the left side and the radius on the right side will cancel out, just give us 1r on the right side. So then our equation simplifies out to, and so then we take the two starred equations that we have. The force of tension equals mass times acceleration due to gravity, and the force of tension is equal to 1/2 mr alpha, and then in this spot equation down here on the bottom is we are going to cancel out the masses, which makes sense because the mass was present in the inertia equation, and so we just needed the mass to simplify the equation from above to give us our 1/2 r alpha. So then we are going to stick all of our variables and terms over onto the left side to equal our angular acceleration, because we're trying to find our linear velocity straight down from the center. And so we're going to end up converting everything over. We're going to figure out a way to convert everything over to our linear velocity. So we have our 2 times the acceleration due to gravity over r is equal to alpha. Our linear acceleration is equal to the, I guess tangential acceleration is equal to the angular acceleration is equal to the angular acceleration, so alpha times r. And we flop that around to alpha equals a over r. The r's cancel out after substituting the a over r into alpha, which gives us our 2g is equal to alpha. I'm sorry, our 2g is equal to acceleration. And then after taking that, after simplifying that, then we just do a and again the radius, it also makes sense that the radius is going away later on too, because like I said, the radius is just inputted for the sake of our inertia, which our inertia is going to end up accelerating the disc downwards quicker. Anyway, so we take our integral of of our acceleration to get our velocity, and we also end up taking the integral on the left side as well in regards to our distance. So we have our integral from 0 to distance s of 2g ds is equal to the integral of acceleration in regards to ds, which gives us our 2gs is equal to velocity. So 2 times the acceleration due to gravity times the distance is equal to our velocity. And that is our whole equation here. Yeah. See if I can get all of it. There we go.